In this video, I'd like to look at one of the more important equations in biochemistry, but also one of the more confusing. And the equation is this one, that delta G equals delta G naught prime plus RT log of Q. Where does this come from? In my experience, students are often very good at using this equation, but then are very puzzled by it. Like, standard state free energy, what does it have to do with anything? How does this relate to equilibrium constants? And so what I'd like to do in this video is try to unpack that. So I'm going to try to unpack this with a specific system in mind. We're going to be thinking about glucose, which is a carbohydrate that is in equilibrium between an open form and a ring form. Just drop it into normal biological conditions and it'll fluctuate back and forth between these two states. The sort of problem that we would use this equation in is as follows. Imagine that we actually look into a test tube and we see that the concentration of open is 0.003 molar and the concentration of the ring form is 0.009 molar. Is the system at equilibrium? If not, which direction is favored and by how much? So we say, aha, this is the equation to use. We need this delta G equals delta G naught prime plus RT log of Q thing. We go look on the internet and we find that the delta G naught prime for this reaction is minus 9.2 kilojoules per mole. We say, well, the Q, that is going to be the ratio of the current concentration of the products to the reactants. So that would be, in this case, the ratio of the ring concentration to the open concentration. We plug in R and T and all of these numbers and we get out, oh, this is minus 6.5 kilojoules per mole. So we've accomplished the task of doing this equation or this thing. But what did we just do? Like, really, like, why, how did that work? Like, we started out with some stuff we measured in a test tube and then we looked up something from a table and we somehow ended up with a delta G. Like, there's a lot of moving parts in there, which actually have some pretty subtle interactions. To set this up a little bit further, I want to spend a moment setting these up molecularly and statistically before digging into some math. So let's think about our test tube for a second that has glucose in it. And we're going to imagine that we've frozen the test tube, or we've frozen time, I guess. The test tube's still not frozen, but time is frozen. And what we would see is we've got a population of molecules, some of which are in the ring form, some of which are in the open form. We can then start advancing time very slowly. As we advance time very slowly, we might see, oh, look, there was a transition. So that molecule just went from being a ring to being open. We keep advancing time and see, oh, look, that one just formed a ring. Keep advancing time. Oh, that one just formed a ring, right? And you could imagine doing this for a long time and watching the transitions that you see between open and ring and open. This is governed by a probability that we set of probabilities, right? So we could say, what is the probability that the next reaction we see in the slowed down universe is open to ring? And then we could ask again, the opposite question, what's the probability the next reaction that we see is from ring to open, right? These are two probabilities governing the sorts of transitions we see in the system. It turns out that the ratio of these is actually the free energy. So delta G can be described as minus RT log of the probability of the forward versus reverse reaction. And in a previous video, I described free energy actually as a bet. We're betting what are our betting odds that the next reaction will be forward versus reverse. And so if our delta G is 0, right here, it's 1 to 1 whether the next reaction will be forward or reverse. We don't know. The odds are exactly the same forward or reverse. If our delta G is minus 20, it's 3,000 to 1 odds that we favor going forward versus reverse. And if our delta G is, plus 20, that's saying that the odds are 1 to 3,000 of seeing a forward versus reverse. So it's really just a measure of this reaction probability, forward versus reverse. Cool. So we got a delta G of minus 6.5 kilojoules per mole. If we plug that into this expression here, what that gives us is that this basically, for every 13 reactions we see going from ring to closed, we're going to see one reaction of opening from ring to open. So in general, we're seeing more forward reactions than reverse by about a factor of 13 to 1. Cool. So that's, in a sense, that's nice, right? We're learning something about the chemistry. But we went from this, which is kind of a puzzling expression, to this thing up here, which I think has some intuitive, even if the mechanics aren't totally clear, the idea of this probability of forward to reverse is hopefully relatively easy to wrap our brains around. But how do we get there from here? And what I'm going to try to do in the next 10 minutes or so is map from the expression that we have some intuition about maybe to this one we have very little, or I had very little about, at least at one point as a student. So the first thing I want to do is, this is going to be, just so you know, it's going to be 5 steps with one sort of wandering path in the middle. So the first step is we're going to write out the probabilities in terms of rates. So what do I mean by rates? I mean, if we're just sitting there looking at the system, we're going to ask, what is the number of times I see open going to ring per second, or the number of events per second? So just sit there and say, every time I see an open to a ring, I mark it down. How often is that happening? And then the reverse rate is exactly the same in reverse. I see how many times do I see a ring turning into an open over some amount of time? So events per second. We can turn this into a probability by the following way. We can say, well, what's the probability the next event I will see as a forward event? Well, that's just the rate of forward events in events per second over the events per second that are forward plus the events that are in reverse. In other words, all events. So the events per second forward over all events per second down here. Can do the same for the reverse, right? I can just say, well, the reverse rate is just the reverse probability is just the number of times I see a reverse per second over all the events that I see per second. If we want to take these ratio, the probability of plus to minus, we would do this, and I'd say, oh man, that looks ugly, but also, hey, look, those denominators are the same and they cancel, which gives us this expression that's saying that the probability of a forward over a reverse is the same as the rate of the occurrence of forward reactions over the rate of the occurrence of reverse reactions. And hopefully this isn't too much of a stretch, right? We're just saying probability of forward over reverse is proportional to the rate of forward over reverse. Okay, so we've done our first move. We've converted probabilities into rates. Cool. Step 2, we're going to unpack that rate. And the way we're going to unpack the rate is we're going to think about it more like a chemist than maybe we've been doing to this point, which is that we have rate constants and concentrations. So we can say that the forward rate is given by K plus, the rate constant, times the concentration of open. The rate constant can be thought of as if I just look at a molecule of open, how quickly does it turn into a ring, right? Just watching one molecule, how often does it turn into a ring? And then the concentration could just be how many open molecules are there, right? So the total rate is the product of these two things. How many things do I have available? How many open do I have that are available to close? And then how quickly does each one of those close, right? Those are the possibilities. That's what that is. We can write out the reverse as just the reverse, right? It's just how many rings are there, that's our concentration, times this reverse rate constant. Okay, step 2 is done. We have now gone from probabilities to rate constants times concentrations. Step 3 is to do some algebra. It's not hard algebra necessarily, but it is log rules. So what we're going to do is we're going to apply the log rule that the log of A times B equals the log of A plus the log of B. And so if we do that, we get the expression down here where now these are now separate, right? This would be A and this would be B. Come on. The next step that we're going to do is we're just going to distribute this minus RT to both of them. And then the last step is actually, if you look over here on this side, notice we have this written as open over ring. That's reactants over products. Chemists really like having products over reactants, sort of an important convention. So I'm applying the log rule here that says the minus log of 1 over A equals the log of A. That if I invert the inside of a log, I can flip the sign out. So basically I inverted the inside, made the ring on top over that, and made this a plus. So this is products over reactants now. Okay. Now, I said there was going to be 5 steps with an aside. This is our aside. This is a nice place to pause. We're not quite to the top of the mountain of finishing this, but we're also at a good place where we can start appreciating where we've gone thus far. So let's stop and think about this for a second. So we've written out this expression that free energy, delta G, equals minus RT log of K plus over K minus plus RT log of concentration of ring over concentration of open. This is cool because the left side depends only on intrinsic chemistry, right? This just depends on the propensity of a ringed molecule, a linear molecule to form a ring and a ring to form a linear. This has nothing to do with the concentration of anything. This is just determined by the chemistry of this carbohydrate. The thing on the right depends only on the concentrations. It has nothing to do with what the molecules even are. It doesn't say anything about which is favorable or not. It's just saying what's the current concentration of these things, right? So we've made a pretty strong separation between two conceptual categories, stuff determined by chemistry and bonds and stuff just determined by concentrations. We're also going to take this and we're going to do another interesting step with it. And that is we're going to say, all right, let's imagine the system equilibrates and that the delta G equals 0, right? Because that is the definition of an equilibrium. The equilibrium is when this free energy is going to be 0. So when our free energy is 0, what can we change? Well, we can't change this part, right? That's determined just by the intrinsic chemistry of the system. Instead, all we can change are the concentrations. The concentrations is the only part of this mathematical system that can change to equilibrate, which means that when we're at equilibrium, this is still delta G, or it's still minus RT log of K over K plus over K minus. This is now the ring and the open in their equilibrium concentrations. We can do an algebraic move. We're going to move this over to the other side and get this, which is now saying that the equilibrium concentrations of ring over open is determined, or is given by the rate constant for forward versus reverse. So it might be easier to see if we actually do a sort of visual model. So imagine that we take these two molecules, the open and the ring, and we put them at 1 molar. Turns out in real life that the closed form, the ring form, is the favorable form under sort of standard biological conditions, which means the rate of going from open to closed is faster. Open to ring is faster than going from ring to open. So this arrow is longer because that direction is favorable. If we put these both at 1 molar and then we let time go, what's going to happen? Maybe if you want, you can pause and think about that for a second. So I'm giving you a chance to find in your device, you paused it. We're unpausing it. This is what's going to happen. The system is going to equilibrate. We're going to get more ring and we're going to get less open. And eventually we're going to reach the equilibrium concentration where there's more ring than open around. And let's actually talk about what's happening up here, right? So at the beginning, the rate constant for going forward for forming ring is faster than the rate constant from going from a ring to open. And so because you have an equal concentration of everything, it's going to start accumulating ring, right? You're going to start getting ring because that rate is faster. But once you get up here, now you've got so much ring around that the back reaction using K minus, even though K minus is smaller, the amount of ring is so high that you start getting appreciable backflow, and eventually you reach a point where delta G equals 0, and we can put it in sort of terms of these equilibrium constants. We can say K plus open EQ equals K minus ring EQ. Right? The forward rate equals the reverse rate because we've reached much higher concentrations. This number is high and this number is low, meaning these two things equal each other. Okay, so what does that mean here mathematically? That's saying that the ratio of K plus and K minus, the ratio of the forward and reverse rate constants, determines the equilibrium concentrations of ring and product, of ring and open. This also means that we can write in here explicitly this expression that delta G, or that this expression also equals minus RT log of KEQ, because KEQ is simply defined as the concentration of ring of the products to reactants at equilibrium. Okay, so I said we were on a side. We're almost done with the aside. Let's try to get back to our main path. So how do we get to a delta G naught prime from where we are? So we were just saying that it's cool that we've broken this expression into a half that depends only on chemistry and a half that depends on concentrations. How do we get into delta G naught prime? So our fourth of 5 steps is to put this thing at standard state. So I already kind of did this, but now we're going to do it in this context. I'm going to say, all right, I'm going to set my open concentration to 1. I'm going to set my ring concentration to 1. I'm going to put it at standard temperature and pressure. And I'm going to say we're at delta G naught prime now. So I've just put it at delta G naught prime. This expression here doesn't depend on that at all, so it just stays the same. But now we've had to substitute in 1 molars over here. Oops, I dropped my RTs. Sorry, RT log of 1. But it doesn't matter because 1 over 1 equals 1. And the log of 1 equals 0. So this whole term goes to 0. What we're left with then is this, that the delta G naught prime equals minus RT log of K plus over K minus. So we've gotten all the way to a delta G naught prime. Delta G naught prime is, I'm going to make myself disappear, all else being equal, which way is favored? If we put ourselves at 1 molar ring, 1 molar open, and let it equilibrate, well, which way is it going to equilibrate? That's given by this expression. That is our delta G naught prime. That is what the free energy would be if we stuck the system at 1 molar everything. If we've set the products and reactants to be the same, all else being equal, which way is favored? Okay, so we now have an expression for delta G naught prime. I've just gone back to our original, this delta G. So this is delta G, RT log of K plus over K minus, and then ring over open. We have our expression we just found for delta G naught prime. Hey, look at that. That's the same as this. So we can substitute that in. We can say delta G equals delta G naught prime plus RT log of ring over open. Finally, this right here is just our products at current over reactants under current conditions. So that's Q. So we've gotten all the way there. We've gone from minus RT log of probability of forward over reverse to this, fun, more standard looking thermodynamics equation. So I'd like to think about what this means in two different ways. The first is, we've already kind of said it, it's that delta G naught prime is a measure of all else being equal, which way will the reaction go? So if I put everybody at 1 molar product, 1 molar reactant, is it going to go forward or backwards? If the delta G naught prime is very negative, it says we favor forward. If the delta G naught prime is 0, it says the reaction doesn't actually care. It can be either forward and reverse are equally favorable. So that's one interpretation. Another way to think of it, and this might actually be more useful in some classes of these problems, is to think of it as delta G naught prime is actually setting the equilibrium point or the equilibrium direction for a reaction. And so recall I said that I said earlier that minus RT log of K plus over K minus equals this, right? It equals minus RT log of the equilibrium concentration of the products over the equilibrium concentration of the reactants. This thing is also delta G naught prime, which says that delta G naught prime can be thought of as the log of the equilibrium reactant over product concentrations. If we substitute that in, and then we also expand Q so that Q is now the current concentrations of ring and open, what that actually shows is an interesting thing. What we're actually looking at here is this is the concentration that we will ultimately flow to, right? This is the equilibrium concentrations of the products and reactants. This is where we are now. If those are identical, if we are equilibrium, if these are the same, this ratio is the same as this ratio, delta G goes to 0, right? It goes to 0 because they're the same. And so what this is effectively doing is delta G naught prime is saying, what concentrations do I have to be to get to equilibrium? Or it's setting the equilibrium set point. And so we can put it more sort of schematically here is the delta G is measuring how far are we from equilibrium at this moment in time. Delta G naught prime is the equilibrium set point. What would equilibrium be if we could get there? It's one way to think about it at least. And this is our current concentrations. And when these two exactly offset each other, you're at equilibrium. When they're not, when this number does not match this number, you're out of equilibrium. So we've talked about ways to interpret delta G naught prime. We've said that all else being equal, which way will the reaction go, forward or reverse? Delta G naught prime equals minus RT log of K plus over K minus. We could also view it as the equilibrium set point. What are the concentrations we're going to reach once we go to equilibrium for the products and reactants? Hopefully what that then gives us is a way to interpret this. When we're sort of plugging numbers into an equation like this, what we're actually trying to do is understand what's our set point, what's the intrinsic direction a reaction will go. When we start adding in Q, what's our current concentration? And together, those tell us whether or not we've reached equilibrium, whether our delta G is in fact 0. Okay, hope that was helpful. It was helpful for me to have to try to think through how to relate these expressions to one another without going too far into the math world. But yeah, hopefully that gives you a way to think about when you're using this equation, delta G naught prime, Q, what these terms are, that delta G naught prime in particular can be understood in a variety of ways as either intrinsic reaction, favorability, or in terms of the equilibrium set point, And hopefully that helps you as you set up and use this equation to solve problems in biochemistry.